Refraction by glass slab. Have you ever noticed a pencil half dipped in a glass of water? Do you know why does it appear to be bent or deformed at the surface of water? It is difficult to guess the correct depth of the pool. The fishermen always aim a little deeper than at the depth a fish appears to be. This is only possible due to change in the path of light rays. It is well known that the light travels along straight line path. But here light rays are bending from their straight line path, due to which half-dipped pencil in the glass of water appears to be bent or deformed at the surface of water. Depth of the pool appears smaller than the actual depth, and the fishermen aim a little deeper than at the depth a fish appears to be. Such examples can be explained by the phenomenon of refraction of light. In general, when a beam of light encounters the surface of a medium or the object, it is transmitted, absorbed, and reflected from the surface. And if a beam of light that is neither reflected nor absorbed but transmitted through the interface of the two media is called transmitted or refracted light, and the phenomena is referred as refraction of light. When a beam of light travels from one medium to another obliquely, it changes its speed at the interface or the boundary of the two media due to change in the density of the medium, and thereby changes its direction also. It can be seen when a light ray enters or leaves a glass slab or glass of water. Moment the ray of light enters another medium, it bends. The phenomenon of bending of light as it passes from one medium to another medium is called refraction of light. But when a beam of light passes from one medium to another, normally it changes speed but not the direction. Still, there is refraction of light. In general, any transparent material through which light can travel is referred to as a medium. How much a ray of light speeds up or slows down in a medium is decided by a factor known as optical density of the medium. The optical density of a medium is not the same as its physical density. The physical density of a material refers to the ratio of its mass and volume. On the other hand, optical density of a material relates to the quantity of light energy that is transmitting through it. For example, density of kerosene oil is less than that of water. Thereby, materially it is less dense than water. But optically, it is denser than water, as can be seen that a light ray bends more in kerosene oil than water. A medium with a comparatively low optical density is called an optically rarer medium, and a medium that has comparatively higher optical density is called an optically denser medium. Let's study refraction of light through a glass slab. First of all, let us discuss some technical terms. A light ray, when approaches the interface of two media, the ray that strikes the interface is called the incident ray, and the one that leaves the interface is called the refracted ray. And the point at which the incident ray strikes the reflecting surface is called the point of incidence. The angle that the incident ray makes with the normal at the point of incidence is called angle of incidence, and the angle that the refracted ray makes with the normal at the point of refraction is called angle of refraction. Here, a ray of light is travelling from air to glass that is optically denser medium than air. Hence, at the surface of glass, the ray of light gets refracted in such a way that the angle of incidence is greater than the angle of refraction. Next, it leaves the surface of glass and enters air again. Since air is optically rarer medium than glass, the ray of light gets refracted such that the angle of incidence is smaller than the angle of refraction. The light speeds up as it passes from a denser medium to a rarer medium. Thereby, the angle of refraction becomes more than the angle of incidence, and the ray bends away from the normal. On the other hand, the light slows down as it passes from a rarer medium to a denser medium. Thereby, the angle of refraction becomes less than the angle of incidence and the ray bends towards the normal. Refraction of light from any medium always obeys some laws called the laws of refraction. According to this, the incident ray, the normal at the point of incidence at the interface of the two media, and the refracted ray all lie in the same plane, and the ratio of the sine of the angle of incidence to the sine of the angle of refraction gives the refractive index of the medium with respect to the air, which is a constant quantity. This relation is also known as Snell's law. Material of optically denser medium has a higher refractive index than that of optically rarer medium. For example, refractive index of ground glass is 1.52 and that of water is 1.33. Therefore, ground glass is optically denser than water. Hence, a light ray bends more in ground glass than in water. Besides the definition of the refractive index given by Snell in his laws of refraction, the refractive index of a medium can also be defined in terms of the speed of light in the given medium. Refractive index of a medium is a numeric factor that tells us how much a ray of light speeds up or slows down in a medium, or how much a light ray bends in the medium. If a light ray is refracted in medium 2, then the refractive index of the medium 2 with respect to medium 1 in which the ray is incident is represented by n/1. It is the ratio of the speed of light in first medium to its speed in the second medium. For example, if a light ray travelling in air and refracted by glass, then the refractive index of glass with respect to air is represented by NGA, which is the ratio of the speed of light in air to its speed in glass. Furthermore, if medium 1 is vacuum and the second medium is any material medium, then the refractive index of the material medium is called absolute refractive index. However, the speed of light in air is almost the same as in vacuum. Therefore, refractive index of a medium with respect to air is also called absolute refractive index. In general, absolute refractive index of a medium is the ratio of speed of light in air or vacuum to its speed in the medium. If N1 and N2 are the refractive indices of the medium 1 and medium 2 respectively, then the refractive index of the medium 2 with respect to medium 1 can be written as the ratio of absolute refractive indices of the second and the first medium respectively. In other words, the product of sine of angle of incident with the absolute refractive index of the first medium is equal to the product of sine of angle of refraction with the absolute refractive index of the second medium. While dealing with refractive index, it should be kept in mind that the refractive index does not depend on the angles of incidence and refraction, but it depends on the wavelength of the light. In the light of laws of refraction, let's relook the refraction by a glass slab. ABCD is a rectangular glass slab. A ray of light is incident at an angle I1 on the face AB of the slab at point L. It is refracted along LM at angle R1. The refracted ray LM coincides on the face CD at angle I2 and emerges out along MN at angle R2. In going from a rarer medium to a denser medium, the ray bends towards the normal, and in going from a denser to a rarer medium, the ray bends away from the normal. Using Snell's law at point L, refractive index of glass with respect to air can be written as the ratio of sine I1 and sine R1. Again, applying Snell's law at M, refractive index of air with respect to glass can be written as the ratio of sine I2 and sine R2. Here, angle R2 is called angle of emergence. It is the angle that the emergent ray makes with the normal. Now, if a plane mirror is held normal to MN, the path MN is reversed and the ray would retrace its entire path. For the reversed ray, applying Snell's law at M, refractive index of glass with respect to air can be written as the ratio of sine R2 and sine I2. Here, it can be noticed that the refractive index of glass with respect to air is reciprocal of the refractive index of air with respect to glass. Since refractive index of glass with respect to air is reciprocal of the refractive index of air with respect to glass, therefore, the ratio of sine I1 and sine R1 is equal to the ratio of sine R2 and sine I2. This shows that angle I2 is equal to angle R1 and angle R2 is equal to angle I1, or the angle of emergence is equal to the angle of incidence. Hence, the emergent ray and the incident ray are parallel to each other. The shift in the path of light is called lateral shift. Let us mark a point P under the surface of a glass slab. If a ray of light from point P incident normally, it would pass without any deviation. If another ray of light from P incident at an angle I along PQ, it deviates away from the normal. It is refracted at angle R along QR. On producing back, QR meets PS at point P1. Therefore, P1 is a virtual image of point P. When we see through glass slab, point P appears at P1. From the triangle PSQ, sin I is equal to SQ upon PQ, whereas from the triangle SQP1, sin R is equal to SQ upon P1Q. Since the light is travelling from a denser to a rarer medium, therefore, refractive index of glass with respect to air is equal to the ratio of sin R and sin I, which is further equal to the ratio of PQ and P1Q. Therefore, the refractive index of the glass with respect to the air is the ratio of real depth and the apparent depth of the object. In general, an object kept in a denser medium appears to be raised when observed from a rarer medium. That is why when a coin is pulled in a trough filled with water, the coin appears to be raised. Also, due to the same reason, a lemon kept in a glass of water appears bigger. The same phenomena can be seen in the case of pencil partially dipped in water. Refraction by spherical lenses. Lenses are commonly used in optical devices such as eyeglasses, contact lenses, magnifying glasses, cameras, etc. In general, an optical device that refracts most of the light falling on it is called a lens. There are two types of lenses, convex and concave. In a convex lens, the refracting surface bulges outward from the lens. Thereby, it is thicker in the middle and thinner at the edges. It tends to collect the light that falls on it. Thereby, it is called converging lens. On the other hand, a concave lens is thinner in the middle and thicker at the edges. It tends to deflect the light falling on it, and hence it is called diverging lens. Convex lenses are further categorized as biconvex lens, plano-convex lens, and convex meniscus or concavo-convex lens. A biconvex lens has both of its surfaces curved outwards, while a plano-convex lens is flat on one side and bulges outwards on the other side. And a concavo-convex lens is curved inward on one side and outward on the other side. In other words, one side is concave and the other side is convex. Similarly, concave lenses are also categorized as biconcave lens, plano-concave lens, and concave meniscus or convexo-concave lens. A biconcave lens has both of its surfaces curved inwards, while a plano-concave lens is flat on one side and curved inwards on the other side. And a convexo-concave lens is curved inward on one side and outward on the other side. It should be noticed that both convexo-concave and concavo-convex lenses have one surface convex and the other surface as concave, but they differ in their shapes and actions. Similar to a convex lens, a concavo-convex lens is thicker in the middle and has a converging action. On the other hand, similar to a concave lens, a convexo-concave lens is thinner in the middle and has a diverging action. If two glass spheres are made to overlap each other and non-overlapping sides are removed, then the remaining overlapped portion can be seen as a convex lens. On the other hand, if two glass spheres are made to overlap slightly on a small glass cylinder and non-overlapping sides of the glass cylinder along with the spheres are removed, then the remaining overlapped portion of the glass cylinder can be seen as a concave lens. In general, a lens is any piece of transparent material with at least one curved surface. If the thickness of a lens is small everywhere, it is called a thin lens. On the other hand, if its thickness is large everywhere, it is called a thick lens. Generally, we use equiconvex and equiconcave lenses. That is, lenses having both the surfaces of the same radii. Let us see the refraction of a light ray at the two surfaces of an equiconvex lens and an equiconcave lens. When a light ray is incident on a lens, its path is altered due to the successive refraction at the two surfaces of the lens. When the light ray is incident on the first surface, it bends towards the normal as the ray is refracted from air to glass. The refracted ray then falls on the second surface of the lens and the emergent ray bends away from the normal as it is refracted from glass to air. In case of a lens, light ray bends at both the surfaces of the lens in the same direction and thereby deviations produced by the two surfaces of a lens get added. It can be seen that a convex lens bends the light ray towards its middle and a concave lens bends the light ray towards its edges. Let us have a look on some basic terms related with spherical lenses. A lens is bounded by two spherical surfaces and the corresponding centers are called centers of curvature. Those are denoted by C1 and C2 respectively. The radii of the two spheres out of which the two surfaces of the lens are formed are called radii of curvatures of the lens and denoted by R1 and R2 respectively. The length of the straight line joining the points of extremities of a spherical lens is called its aperture or the size of the lens. It is also called effective diameter of the lens. A line that passes from the centers of curvature of the two surfaces of a lens is called the principal axis. Geometric center of a lens is called the optical center of the lens. It is a point on the principal axis of the lens such that a ray of light passing through this point emerges parallel to its direction of incidence. It is represented by O, while any light ray entering the thin lens through the optical center emerges out without any deviation. It can be noticed that the principal axis also passes from the optical center of the lens. However, any straight line other than principal axis passing through the optical center is called auxiliary or the secondary axis. Normal to the lens at any point is the line joining the point to the corresponding center of curvature of the lens. A lens has surface of spherical shape, due to which the normal to the surface differs with each point on the lens, and hence it refracts the light at different angles. In general, a lens has an ability to focus the light at a point. A light ray can pass through a lens from either side. Therefore, every lens has two focal points that are located on the principal axis at the midway between the optical center and the centers of curvature. When a set of light rays passing through a point or starting from a point on the principal axis after refraction through a convex lens becomes parallel to the principal axis, the point is called its first focus. It is on the side of incident rays. On the other hand, when a set of light rays moving towards a point on the principal axis after refraction through a concave lens becomes parallel to the principal axis, the point is called its first focus. Now it is on the side of emergent ray, and the distance of the first focal point from the optical center is called first focal length, which is denoted by F1. A plane passing through the first focus and normal to the principal axis of the lens is called first focal plane. When a beam of light rays parallel to the principal axis falls on a convex lens, it focuses the incoming rays at a point on the principal axis called its second focal point or second focus. It is on the side of emergent rays, and if this beam of light falls on a concave lens, it refracts the light outwards in such a way that the light rays appear to diverge from a focal point, which is the second focal point for the concave lens. It is on the side of the incident rays, and the distance of the second focal point from optical center is called second focal length, which is denoted by F2. Similar to first focal plane, a plane passing through the second focus and normal to the principal axis of the lens is called second focal plane. In general, the medium on both sides of a lens remains the same Therefore, first and the second focal lengths are equal numerically. Usually when we say focus, we mean second focal point. It is also referred to as principal focus or principal focal point. Thereby, when we say focal length of a lens, we mean second focal length. It is also referred to as principal focal length, and the distance of the principal focal point from the optical center is called focal length, which is denoted by f. For a convex lens, focal length is always positive, and for a concave lens, it is always negative. A convex lens has a real principal focus as the refracted rays actually meet at that point. But a concave lens has a virtual principal focus as the refracted ray appear to diverge from that point. Only a beam of light rays incident parallel to the principal axis after refraction through a convex lens converges to a single point on the principal axis, that is, the principal focus. But if the beam of parallel light rays incident obliquely, it does not converge at the principal focus. Rather, it converges at a point in the second focal plane of the lens. Similarly, when the beam of parallel light rays is incident obliquely on a concave lens after refraction, it appears to diverge from a point in the second focal plane of the lens. Any transparent material with curved surfaces can be used as a lens. The same can be verified while observing through a glass of clean water. Here, water is bound by curved surface and it behaves like a lens. If we place an object behind this water lens and have a look at the object through the glass of water, one can see the magnified or enlarged image of the object. A drop of water also behaves as a convex lens. When a plant leaf is viewed under such a lens, it is seen magnified. What makes a lens different from any other transparent object is its ability to focus light. Most of us are familiar with the ability of magnifying glasses to concentrate sunlight to a point where it can burn a paper. Though it is only half true that a lens can concentrate sunlight to a point that can be used to start a fire. Only one type of lens, that is a converging lens, will do that. And the point at which the sun rays concentrate is referred to as focus of the magnifying glass. Let us now understand some of the applications of the lenses. An optical device that is very close to many of us is the spectacle which we use to aid the vision of weak eyesight. Spectacles are able to help the vision of the people with weak eyesight. The person who finds difficulty in clearly viewing the distant objects is suggested to wear concave lenses of the desired focal length. The person who suffers difficulty in clear viewing of nearby objects is suggested to wear convex lens of the desired focal length. Generally, a palmist or a jeweler uses a hand lens to see the magnified views of the lines in a hand or a jewel stone. It is nothing but a convex lens used to see magnified images of the objects. However, a combination of two convex lenses of different focal lengths is used in a compound microscope, which is commonly used in laboratories. It is able to produce a highly magnified image of very tiny objects that may not be visible with the naked eye. A combination of two convex lenses of different focal lengths is also used in a telescope. Though a combination of a convex lens and a concave lens is also used in telescopes, it enables us to see a clear image of a very distant object. Binoculars are nothing but a pair of telescopes. Finally, let's see the difference between a convex lens and a concave lens. In contact with their shapes, a convex lens is thick in the middle and thin at its periphery, while a concave lens is thin in the middle and thick at its periphery. A convex lens converges the light rays towards the principal axis, while a concave lens diverges the light rays away from the principal axis. A convex lens has a real focus, whereas a concave lens has a virtual focus.